So we want to create this function convolution self-made, where the input arguments are an image, the set of filter, and then we can also set the padding and the stride length. So the structure will be, so the first part of this code will be almost like the first part of the previous code we wrote. So we just need an image, of course, so we can just copy and paste this part. And we also want to show the image then. And then after this part, we want to add the actual convolution part. So therefore, we need the size of the incoming image and the number of channels. And also we need the size of the kernel because we want to perform convolution. And remember the equation I showed earlier, where we could determine the size of the output image based on the size of the input image and the kernel and the padding and the stride. And that's what we have to do now. And that's why we need all these parameters here. So once we have these parameters, we now know already how large the output image will be. So we initialize, or we just first of all determine the size, so X and Y. And then we initialize the matrix for the output images. And then we, if we have padding, we initialize the padded image based on our input image. And if padding is 0, then the size of the padded image will be exactly the size of the input image. Then padding here is 0, and they have the same size. So then we take the input image and put it into the padded image. So if padding is not 0, then our input image will be in the center of the padded image, and the edge of the padded image will correspond to the actual padding. And again, if padding is 0, then both images will have the exact same size. So we padded the image, we determined the size of the output image, and therefore also pre-allocated already a matrix for the output image. So then we have our padded image. I just want to remind you on this parameter. So that's the edge of the image, to say, then the total size is 2 times padding plus the image. So that's actually, that's exactly what you see here. And of course, we want to do this for every channel, so for every color channel. And then the actual convolution part will take place. So we want to do this manually because we want to understand how convolution really works. And as explained in the previous slides, it's a multiplication of the image with the kernel, and then we sum up those values. So we have to walk through the image and X and Y coordinates, and then we have to do this for the different channels. So we need at least 3 nested loops for each image. And how do we find the coordinates? So if we are in the coordinate system of the output image, then our X and Y coordinates run through the output image. And then we can just determine the start of our window by the current coordinate and the stride length, and also the end of our window by the current coordinate, the stride length, and also the size of the kernel. And I want to illustrate this in the next slide, that it becomes clear how that actually works. So then we have the start and the end coordinates of our, let's call it current slice, where we want to perform the multiplication. So we just extract this current slice from our image, and we multiply this with our kernel, and then we sum it which is just the convolution, and that gives us the value for the output image in the new image coordinate. So I want to show this graphically that everyone understands how that works. So we work in the coordinates of the output image. So let's say that's our image here. And let's start with a stride length of 1. So we're starting here. And the size of the kernel is 3. So the start value, let's say in Y, for example, is then the current coordinate times stride. We would start at 0, so we're just right here. And then the end coordinate is the current coordinate, which is still 0, times stride plus the size of the filter. So then you're here. And the same, of course, applies for X. So that just covers the entire region here. We will take these coordinates then, cut out the slice of the current image, and multiply this with our filter. And then we will get the value for the output image. If the stride is 1 and we continue the next step, then this coordinate will be 1. So we start at 1. Then the end coordinate will be at 1 plus the size of the kernel. So it's exactly what you see here. And so on. What if the stride has a different value? So what if the stride is 2? Again, we would start at 0 because we always start at 0 because we are in the coordinates of the output image where we apply the padding already. So for stride 2, we would be at 0 here. And the end coordinate would be 0 plus the size of the kernel. So it's still the same thing. Again, we don't need to worry about the padding anymore because we started at a padded image already. And because that's the coordinate system of the output image. So now stride is 2. What does it mean? And next coordinate, Y would be 1 because that's the next step in the output image. And 1 plus times 2 would give us a shift of 2 in the original image. Now again, always take into account that we are in the coordinate system of the output image. So in the output image, Y starts at 0, and then Y equals 1. But in the input image, it's Y times the number of strides, or times the stride length, and then you're here. And then you just add for the end coordinate the size of the kernel again, and then you're here. For the coordinate Y equals 2 in the output image, in the input image, we would have to go to 2 times 2, which is 4. So that would be the next step. And that's what you see here. And we just maintain the stride length of 2 and so on. So I hope that is clear now that we work in the coordinates of the output image where we applied the padding earlier. So we always start here in the upper left. And then we go through the coordinates in the new image. And what we do here is calculating the start and the end coordinates in the input image, what I have illustrated here. And finally, I also want to show this for stride equals 3. So again, it's the first entry in the output image. So that would be 0, 0, size of the kernel. Again, we are here. And again, it's always in the upper left because it's the padded image already. Then in the next step, Y would be 1. So it's 1 times 3. That would be here. And the end coordinate would be 1 times 3 plus the size of the kernel. So they would not overlap. And again. All right, so now we convinced ourselves that our routine would work. And then we do that for all the different channels, and therefore we will have a convolved image for all three color channels. And we want to plot and display this image as a grayscale image. So we just sum up over all color channels and then see what this image looks like. By the way, that's what you actually really do in an ANN. So you run the convolution for one filter over the different color channels, and then you just sum it up, and that's the result. That's the output image from the first convolution filter. And you do that for all the other convolution filters. So the output matrix will have a shape which is the size of the output image times the number of convolution filters. And of course, we want to add the title and then plot this image. So that's the idea. And therefore, I think we are ready to go back to our Spider user interface. And we want to create this function. And then also want to explore a bit the results when we apply different filters. So we just, I would say, add a new function. We can actually go to my convolution. We just copy and paste this part here. And let's call it convolution self-made. And later we will take this part we will take this function and add most of the code to our neural network because then we can already implement the forward part of our convolution filter. So again, we want to have the image as an optional input argument. So now we want to feed in the filter, the padding, where we set the default value to 0, and also the stride, where we set the default value to 1. So all right, then we can just copy this part here. And then we determine the size of the shape of the image. So we have X, Y, and the number of channels. And we get this information from image shape. Just to remind you, we have this image I, and then we want to determine the shape. Let me just call this image again. So we always have the structure here. All right, so we go to our convolution self-made, determine the size of the image. Maybe I should write it down. Shape of input image. Then we also need the shape of the kernel. So we call it just xk, yk, and then that's k shape. We have our k Yeah, so we just, of course, K is one particular filter. So, for example, it could be K1, and then we can determine the shape of K1. Okay, so because we want to do this, so because that's just one particular filter. Okay, so now we determine the size of the output image. So first, I would say we're just calculating X and Y. So we just call it X output. And then we just apply the equation. So what is the equation? So it's the input, the size of the input image, minus the size of the kernel, plus 2 times the padding. And we take this and divide it by the stride. And then we just add 1. And that's the equation we just have derived. Yeah, we just have derived earlier. Yeah, and we just want to make sure that it's an integer. And we're going to do the same thing for y. So let me also just label it with that. So we have our image. Which is called I here. That's our image. Then we have the difference. Then we have the size. 188 times 199, I think, was the y value. And you see there's a typo, so let me just remove this typo here. And let me just run it again. Okay, so then we have X shape, so X image shape and Y image shape. All right, so we remove the typo. And then we now can calculate the size of the output. So let's say we have padding equals 2 and stride equals 1, and then we can calculate those values here. And xk was the size of the kernel. So let's, for example, take k1, which is 3 times 3. And now we can determine the size of the output image. Okay. And you see, it always makes sense to check this outside, because as you've seen there always can be typos. Okay, so now we have the size of the output image. And since we have the size of the output image, we now can pre-allocate a matrix for the output image. So what is the size? So we want to, first of all, save the convolved image for all different channels. So we just say number of channels. So now we want to add this image. because we want to move in the coordinate system of this particular image. So first we create the matrix for the output image. And then we can create the padded image. And also here, we want to do that for all color channels. And if we want to create the padded image, remember, it's the x coordinate plus 2 times the padding. And you do that for x and y. So now we have prepared the padded image. That's our output image, which is still empty. And the padded image is also still empty, so we have to put the actual image in the center of the padded image. So the idea is that you just go to the padded image and index the padded image. So we also want to make sure that it's integers. So we just go from the padding, that's the one edge, let's say on the left-hand side, to padding plus x im shape. Now remember, you added the padding twice because it's you added left and right and top and bottom. That's what you do here. And now we just put the image in the center. So between left to the first padding layer and the second padding layer. And we also want to do that for y. And let me do the line break here. And we want to do this for all the color channels. And again, so I determine the size of the output image, then I pre-allocate the matrix for the output image. Then I also pad the image by creating an empty matrix where the shape is the x and y shape of the input image plus 2 times padding. And then I put the image in the center of the padded image. So now we're ready for running our loop. And we want to do this in a nested, in a set of nested for loops, which of course is by far the slowest way how you can do that. So you should, of course, if you really want to improve runtime, use commands like nptile or something like that. I want to do this in a set of nested for loops that it's really clear to you what the code is actually doing. The code will be then like 50 to 100 times slower actually compared to a fully optimized code. If you want to compare it to TensorFlow, it's what we do in the last chapter. So we compare our convolutional network to one from TensorFlow, where we have the exact same settings, and we will see our code will be kind of 100 times slower. And it's because of all these for loops. But as I said, I actually want to write this in for loops that everyone can see what the code actually does. And maybe it's a nice homework for you to use once everything works, that you use other commands like tile and improve the code concerning runtime. Okay, so let's start for the channels. So let's start for the color channels. So we just run over all channels. And then we run over the coordinates of the image and of the output image. By the way, the order of the nested loops doesn't matter as long as you keep the indices consistent. So what would we do now? First of all, we want to find the corners of the current slice. So let's call it y start equals y times stride. That's the start. And then we have y end equals y start plus yk. I need to do the same thing for the x coordinate. Let me just check numChances. Not defined. How did we call it? numChan. Okay. So then we have the current slice. In the padded image. So now we have to be careful with the coordinates. Of course, first you have the x coordinate. Oops. Then you have the y coordinate. And we want to do that for all the color channels. Sorry, for the specific color channel. That's what I meant with the indices. As long as you're consistent within the indices, then the order of the loops doesn't matter. So then we calculate the result by using NP multiply, the current slice times our filter K. And it's an element-wise multiplication. And now we have our output. And here, that's the point where we have to be consistent. That's, of course, now X, Y, Z. And again, that refers to the coordinates of the output image. And then we just sum up all those values. yeah, that's actually it. So now we just fill the matrix with all these values, and after the loop, we are done, and we can create a plot. And we create a plot of the output. And we sum it over all color channels. So which is coordinate 3, which has the index 2 in Python. And we want to display it as a grayscale image. Yeah, I also want to add a title. So let's just quickly add the title. And and we also want the to return this image. So we also want to have an output, this image as an output argument. Okay, so let's try that now with our particular image that we have here. So let's go to the plots. Let me maybe just delete this part here. So those images that we keep our original image. Well, actually, we also showed the original image, so we can also actually delete everything. So let me just compile the code, and then let's see whether we get an error message or not. So we have convolution self-made. We leave the image as it is. And let's try it for a particular kernel. So we have, let's say, our kernel, let's say K1. And then let's say, yeah, let's keep the default values in the first try. Let's see what we get. To say what we want to do. And there's another typo. That's this one. So it says it's not subscribable. Of course it's not, because it's a method. It's not a vector or something, or an array. All right. Of course so Python is always right. Okay, so now we have our filter. We have the output. So that's the original image after convolution with padding 0 and stride 1. And we have our output image here. Okay, let's try it with a filter where we can see a difference. It was the blurring filter, and there's another filter which was blurring, and let's also try another filter. So let's actually stick to this filter. Okay, so now we have our image here. Let me delete this again. And then we have our output image. And let's now do it for different values for the padding. So for example, let's say padding equals 2. Then the image should be larger, and you actually see the edge here. That comes from the padding. So let's just add some absurd value that we really see the difference. And here you can see the padding of the image. And we also want to check for the stride length. So let's go back to set padding equals 0 and stride equals 1 was default. Let's say 3, which is the size of the filter. And that should actually give us an image which is smaller. So again, that's the original. It goes from 190 to 200 roughly. Here you see padded image, it's larger. And if I apply padding 0 and a large sprite, I should have fewer data points for the output image, so it actually should be smaller than the input image. So let's see whether that works. And in fact, it does. You see, it's a roughly a third smaller. If you compare it to the input image, so like 200, and here you have 60 something. And of course, it's blurred because you have fewer pixel in the image. Actually, there's one thing you can see that the plants in the background and also the street here in the foreground, they're more visible than the dark and the background, what you can see here. So they kind of blur into each other. So that could be, for example, a filter recognizing structures like what you see here in the plants. And you can also do that with different filters, of course, to just have another value, another filter. We see another result. You see it's different. And that's the idea of the convolution filters. So they can focus on different features. And again, those filters or the values in the filters will be what's going to be learned by the neural network. All right, so we convinced ourselves that our convolution part works. So let me just go back to the PowerPoint. So we have our self-made convolution routine, and we return the output image, and we can try different kernels. So just whatever you like, and really play with some values that you get an idea about the function itself, and also make sure that the result you get makes sense. By the way, also here, I used one of those filters, Stridus5, and then you can see here that the background objects all disappear, and what is left are the foreground objects. Now, that's another idea how to separate the background from the foreground, and they're completely different. And that's also something a neural network might be able to learn. Also here, you should see the padding. Okay, so now we're ready, almost ready for including this convolution part in our neural network package. The problem now is that we actually have to do one thing first. So in the first part of this lecture, where we had just a matrix with data points, we were able to feed in the entire matrix for every epoch. Now the problem is every image is a matrix of considerable size, and we have thousands of images. So if we would just take all those images and put it in the network at once, then our computer would just crash. It would be very inefficient. It would not work at all. So the idea is that we randomly select so-called mini batches, which are subsamples of the large data set, and then process those mini batches through our network for every epoch. Do this several times, and then randomly pick another mini batch. So we have to add a routine that does the job for us and selects mini batches of particular sizes, like let's say 64, 128, and 256. So we have to set up a routine that selects these images, creates the mini batches, and then feeds it into our convolution part. And then we have our convolution part, and we have to add a few more things, and then we still have to find a way how to feed this information into our actual network. And also we have to take into account that all those images have different sizes, but the network has one particular size. So that also means we have to scale those images to all to one particular size. So we have to rescale all the images, and then we can feed them into our network. So we have to perform these two steps. So writing a routine that selects the many batches randomly, and it performs the rescaling that we can feed it into our network. And that's what we're going to do next. So we have to do these two things first.